This lesson will cover on reversible reaction and concepts on chemical equilibrium.
Reversible reactions are reactions where formed products can revert or go back to their original reactants. Since the reaction can proceed in either direction, we use this reaction arrow to represent reversibility. An example of a reversible reaction is the thermal decomposition of ammonium chloride to form ammonia and hydrogen chloride. Place ammonium chloride in a boiling tube and heat using a Bunsen burner. Ensure that this is conducted in a fume cupboard, as ammonia and hydrogen chloride are both corrosive gases. If we hold red litmus paper at the mouth of the boiling tube, it turns blue, which confirms the presence of ammonia. Blue litmus paper turns red, which confirms the presence of hydrogen chloride. Remove the boiling tube from the heat and let cool. Have a look near the mouth of the boiling tube. You will see that there are white crystals. These are ammonium chloride crystals. So what has happened here? Ammonium chloride has thermally decomposed to ammonia and hydrogen chloride. The formed ammonia and hydrogen chloride have reacted to produce ammonium chloride. Therefore, this is a reversible reaction.
Consider this reaction, where nitrogen reacts with hydrogen to produce ammonia. As nitrogen reacts, the concentration of nitrogen and hydrogen would gradually decrease over time, and the concentration of ammonia would increase over time. And as it is being observed here in the graph, there will be a point where the concentration of ammonia, nitrogen, and hydrogen becomes constant. And at this point, it is said that an equilibrium has been achieved. This is only possible if this reaction is occurring in a closed system. What if this reaction occurs in an open system? As ammonia is being produced, as nitrogen and hydrogen gas reacts, the ammonia would escape to the surrounding. Since it escapes, only the forward reaction would occur. The reverse reaction is unlikely to take place, as there isn't any product to cause the decomposition of ammonia to produce nitrogen and hydrogen gas. Thus, an equilibrium is only possible to achieve if it is a closed system. Let's look at the rate graph. Reactants are being supplied in a reaction. Thus, the rate of forward reaction is very high initially. So, rate of forward is very high. As reactants are being consumed to form the product, the rate of forward reaction would gradually decrease as reactants are being consumed. As the concentration of product gradually increases, the products can break down to form back the reactant. This causes the rate of reverse reaction to gradually increase over time. There will be a point where the rate of forward and reverse reactant meet, and it is said that the system has reached equilibrium. As indicated, the arrow shows where the system has reached equilibrium, where the rate of forward is equivalent to rate of reverse reaction. So what is chemical equilibrium? It is a dynamic chemical process that happens only in a closed system at a constant temperature. What does it mean by dynamic? Dynamic refers to a system which is keep converting the reactants to product and products to reaction. In other terms, it means that the reaction does not stop. And when a system has reached equilibrium, we say that the concentration of all species are constant. This could be shown from the concentration graph where the concentration of reactant and the product will become constant over time when system has reached equilibrium. The rate of forward and reverse reaction will become equal. As what we have seen earlier, the rate of forward and rate of reverse reaction would meet when the system has reached equilibrium. And the macroscopic properties will become constant. And some of the examples of macroscopic properties are pressure, volume, density, color, pH. And all these properties would remain constant. Let me give you an example of an equilibrium system.